figure 2.11. Determine A, the particle's speed at t is equal to 10 seconds and at t is equal to 20 seconds. Then B, the distance traveled in the first 20 seconds. Alright, so how I like to think of this is that since this is a function of acceleration, we can actually end up realizing, and go back to a bit of calculus right here, that we can say that, hey, isn't the definite integral of the acceleration function of, say, a of x going to be the same thing as v of x, or the velocity of x, as in you're going to go in a step back? Well, of course, what you need to know is the definite integral is just an infinite sum of tiny, tiny little rectangles, which means that the area under that curve is going to be, if this was going to be, say, y is equal to ax, the area under that curve is going to be the value of v of x. So if you're going to go from 0 to x, that means that's going to be the value of v of x for that curve area. Now, in our case, we have it pretty good because this is just a really simplified function where, using our knowledge of geometry, we're able to find the area under this curve stupidly fast. It's just really convenient what they throw at you. So, for A, now that we know our little lesson about definite integrals, we can say for A, the particle's speed at t is equal to 10 seconds. Well, what we can then say is from 0 to 10, we want to find that area under that little rectangle right there from 0 to 10. So then 10 seconds times 10 meters per second squared, that's going to be equal to 20 meters per second. So we already have that done, because that's the total area under the curve of that function. And at t is equal to 20 seconds, well, you see that during this interval there's no acceleration going on. So that's having an area of 0. However, here, we know this is actually going to be about 5 seconds, because, 20 minus 15, that's the delta, times 3, negative 3. So from 20 seconds, that means we have to add up the net area, meaning we have to find the positive area and, of course, the negative area. So for A2, what we're going to end up doing is we're going to say, okay, so that's going to be 20 plus negative 15. Therefore, that's going to be 5 meters per second at t is equal to 20 seconds. And it makes sense because, as you're going through this, you have this positive rectangle, and you're getting, of course, you're getting a positive velocity, but towards here, your velocity is slowing down due to here, so you have to make sure that the net change is properly calculated. All right. So for B, the distance traveled during the first 20 seconds, so what I'd like to be able to do is you just split this function into small parts, because then what you can end up doing is you could just calculate the delta x between these parts right here. So for this answer, all you have to do is just sum the change in x in between these functions right here. So for part 1 of B, what we'll do is, of course, it says it starts from rest. Therefore, v initial is going to be equal to 0 meters per second squared. Right? Then, of course, our acceleration is going to be 2 meters per second squared, and t is equal to 10 seconds. Then we can use our nifty kinematic of delta x. It's going to be equal to 1/2 at squared plus v0t. Then we can just plug in, which is going to be equal to 0.5 to 100, then plus 0. And that ends up being 100 meters. So our first part for part 1, that's going to be 100 meters. Secondly here, so as you can see, for part 2, we don't seem to be having an acceleration here, but that doesn't mean the velocity is 0, because this particle was accelerated through the first part. So after it's leaving here, this is going to have an initial velocity of 20 meters per second. Because what ends up happening is that you're leaving this with an acceleration, but it's just, as this goes to 0, you're just going to have a constant velocity. That's all that means. So we can say that v0 is equal to 20. And using our kinematic again, we can say that delta x, that's of course, so we're going to have 1/2 acceleration of 0, and then, 25. But that goes to 0. What interests us is, of course, v0t. So that's the same thing as 20 times 5, which is equal to 100 meters as well. So right here we have 100 meters. So then, for number 3, the final part, we realize that we're going to have a negative acceleration and that our velocity, initial, is still going to be 20 meters per second because in the second part, there is no acceleration in our velocity. So we can still say v0 is going to be 20 meters per second. In this case, acceleration is going to be negative 3 meters per second. And t is going to be equal to 5 seconds in this case. It matters. Oh, here we go. Now, we can just plug in that same equation. So delta x is going to equal to 0.5, negative 3, 25, plus 100, because, we have v0t. So that's going to be equal to plus 100. And that ends up being equal to 62.5 meters. So now we just add the change in x up, which is going to be 262.5 meters. Bam, we did it.